Alright, this is a video for activity 7B of the ESA Study Guide Level 3 Physics. So question 1, in the game of billiards, players frequently bounce a ball off the edge of the table called the cushion. That's the edge of the table. The edge is called the cushion, not the table called the cushion, in order to achieve a better angle for potting another ball. On one occasion, a billiard ball with a mass of 50 grams, seems unlikely, but so 0.050 kilograms, travels with a momentum of 0.105 kilogram meters per second toward the cushion and bounces back with momentum of 0.095, and the impact lasts for 0.011 seconds. So the question is to A, draw a vector to show the direction of the change in momentum of the ball. So the change in momentum equals momentum after minus momentum before. So the momentum final minus momentum initial. And the momentum initial was toward the cushion, and the momentum after is away from the cushion. Let me just put this in a slightly better way, actually. So PF is away from the cushion, PI is toward the cushion. Now this can be reframed as delta P equals PF plus negative PI. So instead of saying the final momentum minus the initial momentum, we'll call it the final momentum plus the negative of the initial momentum. And negative PI, if PI is that way, negative PI is that way. Same magnitude, different direction. So delta P equals that plus that, which is that. Okay. Calculate the size of the change in momentum of the ball. So we know we're just adding together the two momentum magnitudes based on our vector diagram here. So delta P equals 0.105 plus 0.095, which is 0.200 kilogram meters per second. Part C, calculate the size of the average force on the ball. Now, the thing you need to remember is that the impulse force, or the impulse, the change in momentum, equals the force applied during the collision multiplied by the amount of time that the collision takes. Now, we've got this bit here, 0.200 equals F times, and we've been given the amount of time, 0.011. F equals 0.200 divided by 0.011, which is, well, you notice when I'm doing this, every time I'm writing down the equation before I go to attempt to plug things in to solve it, and that helps to cement the equations in your memory. Whoops. And what I want to do here is round it to the right number of significant figures. We had 2. So in the problem we've got 3 significant figures for 1, mostly 2 significant figures. So we'll go for 2 significant figures. 18 newtons to 2 significant figures. On another occasion, the ball travelling with a momentum of 0.10 kilograms per second rebounds at right angles with the same momentum. The ball is in contact with the cushion for 0.050. So this time it's going this and then this. So we've got PI and PF, and we're going to do the same thing. We've got delta P equals F minus Pi, which equals Pf plus negative Pi. Now let's substitute in as we go. So delta P equals, so we've got this one. And then we've got negative Pi. And we've got to put some numbers on these to make this a little easier before we add them together. So it says rebounds at right angles with the same momentum. So this is still 0.10. Alright. And now we've got to actually do this addition. Oh, this is D1, by the way. So we don't have to do the addition completely. We've just been asked to draw a labeled vector diagram to show the direction of the change in momentum. So delta P, so we go this one, this one, oops, sorry, that was P final. This is negative Pi, also 0.1, and therefore this one is delta P. Okay. To show that the size of the change in momentum of the ball is 0.14. Well, here's our diagram. And we just want to use Pythagoras' theorem. I forgot to put an important thing on this diagram. This arrow here, the ball rebounded at right angles. That's a key aspect of it, is a right angle here. So we're going to use Pythagoras' theorem. So delta P, this is the magnitude of it, equals squared equals Pf squared plus Pi squared. Delta P equals the square root of 0.1 squared plus 0.1 squared equals the square root of 0.02, which is 0.14142 or 0.14 kilogram meters per second to two significant figures. So we have to remember every time we give our answer, we give it rounded to the right number of significant figures and the correct units. And when you do one of these show that questions, what you're aiming to do is to include an answer that included more significant figures to show that you've done all of the working, and then round it to the correct answer. Calculate the size of the average force that acts on the ball. Well, if delta P equals Ft, F equals delta P over T, which is 0.14 divided by, and it was in contact for 0.050 seconds. Gives 2.8 newtons. Part 4. Explain why the direction of the force on the ball is the same as the direction of its change in momentum. Okay, we need to think about here, I think, what momentum is. So momentum is mass times velocity. Velocity is a vector. Now, most importantly, acceleration results in change of velocity in Newton's first law. Acceleration is result of unbalanced force and is in direction of force. Therefore, change in momentum is in direction of the unbalanced force. So the change in momentum is a result of acceleration, and the acceleration is in the direction of an unbalanced force, so the change in momentum is in the direction of the unbalanced force. That's the explanation I would give there. Okay, clear that. Whoops. All right. Question 2. During a docking maneuver, a spacecraft of mass, let's write a few things down as we go, 5.0 times 10 to the 3 kilograms, moves toward a space station with a momentum of 1.5. So the magnitude of pi is 1.5 times 10 to the 4 kilogram meters per second. The direction of the craft has to be changed by 90 degrees. To do this, the maneuvering rocket, which delivers a thrust of 3,200 newtons, thrust is a force, so 3,200 newtons is fired for t equals 7.8 seconds. Calculate the size of the impulse given to the spacecraft. So at this point we're not being asked for the direction, for the size of the impulse. So the impulse is the change in momentum. So delta P equals Ft equals 3,200 times 7.8, which is 24,960 Newton seconds, or more importantly, it's a change in momentum, so kilogram meters per second. Part B, draw a labeled vector diagram to show the direction of the force of the rocket. Well, what we know is we've got the delta P equals to the initial momentum minus, so whoops, go back a step, Logan. This is one reason why it's super important to write the formulas down, because it gives you a chance to pick up when you're doing them wrong. Delta P equals P final minus P initial. It's kind of important, which is the same thing as P final plus negative P initial. Alright, P final, according to the diagram in the book, is this way. P initial, according to the book, is this way. Like when I say according to the book, I mean the diagram that's in the question. Therefore, this is delta P equals this plus, and then the negative of that is the arrow going to the left. And it's just changing its direction. It's not actually changing its speed. So the magnitude of the momentum is going to be the same. So now they wanted a labeled vector diagram. So to get to this, so we need this plus that equals that. So this plus that equals that. and they're at right angles to each other. So this is PI, no, sorry, PF, negative PI. And we can put some amounts on here. 1.5 times 10 to the 4, also 1.5 times 10 to the 4. All right, so this is this one. This arrow here gives you the direction. Now these are the same length, so this is going to be 45 degrees. Part C. Calculate the size of the momentum of the spacecraft at the end of the maneuver. All right, so we're just going to solve for this. Actually, we don't know that that's true, do we? Now that I look at this, we've been given an impulse force and so on. We've been given a change in momentum vector here. I've got that wrong and that wrong. So if you have watched that previous part of the video, you need to undo what I just did. So well, this should be correct, but obviously what we know here is actually that delta P, there it is there. We can work out this angle, and we'll do that. I don't know if it's required, but we'll do that. We can work out this angle here, for example, Sokotoa, so let's just choose another color. So if that's the angle, we'll call it theta, and this is the adjacent, and the long one here is the hypotenuse, and we've got Sokotoa. So what have we got? They've got the angle, so sine of the angle equals the opposite, that's that one, we don't want that one. Cosine of the angle equals the adjacent over the hypotenuse, so it's this one. So cosine of theta equals the adjacent, 1.5 times 10 to the 4. Actually, you know what? I've done that wrong too. See, even I'm going to make mistakes while I do these sometimes. The difference might be that I realize I'm going wrong and pick them up as I go. Let's try this again. All right, which one do I know? It's not actually that one, is it? I'm going to just put back this. Because when I think back to the beginning, I actually knew the initial momentum. I didn't know the final momentum. So the one I can actually draw in is not the final momentum. It's this one here. Okay, so now I use my Sokotoa, and I'm going to find, I think that instead of being cosine, it's going to be sine. Sokotoa. Again, you know, if you need to write these things down every time, do, because it helps you remember them. So sine of the angle equals the opposite of the hypotenuse. That's the one I want. So therefore, sine of theta equals 1.5 times 10 to the 4 divided by 24960, which is 2.5 times 10 to the 4, but we'll just use it as it is. Now, make sure when you're doing these sort of things, you're using your calculator correctly and using the times 10 to the x button, or the exponent button, rather than typing in times 10 to the power, raised to the power 4 or whatever, because you'll end up with the wrong answer. So theta 601 Therefore, theta equals sine inverse of 0.601, which equals 36.9 or 37 degrees to two significant figures. And C, calculate the size of the momentum of the spacecraft at the end of the maneuver. We can use Pythagoras' theorem for that. So delta P squared equals PF squared plus PI squared, just solving off this triangle, same as before. So 24960 squared equals PF squared plus 5 times 10 to the 4 squared. Same thing as before. You need to make sure the order of operations works here, so make sure you use your exponents button. Plus and I get that, I've mucked it up. I added the two together. It wasn't, whoops. It wasn't very helpful there. I needed to subtract that from this, not add it. So let's just do it properly. Oops. PF equals the square root of 24960 squared plus 1.5 times 10 to the 4 squared. Now try it. I've done it again. It's not plus, is it? It's minus. Minus. Why I'm picking this up when I go to do the calculation is I'm realizing that my PF has been greater. The number I'm getting is larger than this number here, and that cannot be true. And it's basically because I keep not subtracting. I kept on adding the two together inside this, not subtracting it. And this time I get something more realistic. 19949, which is 20,000 kilogram meters per second to two significant figures. Now you can reframe that as 2 times 10 to the 4. It's actually 2.0 times 10 to the 4 kilogram meters per second to two significant figures. So the reason we can do this is if we think of the decimal point, if I keep moving the decimal point this way, basically this is 2 times 10 to the 4, which is 10,000. So 2 times 10,000 gives 20,000. Okay. That was a bit messy, wasn't it? Alright, question 3. This has got a whole lot of graphs. A glider is propelled into the air by devices which have different graphs of force against time as shown, and the force F becomes 0 in all cases after the same time t. Which one of the devices would transfer the greatest momentum to the glider? So here's the thing, delta P equals Ft. That's based on the idea of a constant or average force. So we're looking for a situation where the average force is the highest, for the highest momentum. So for highest delta P, the average force must be highest. Now, the average force equals the area under a force versus time graph divided by the time. Well, actually, yeah, when I say the highest delta P For the highest delta P, the average force must be highest. That's because they're all with the same time, where time is same for all options. So let's just include that there. The average force equals the area under the force versus time graph divided by the time. See the total delta P. We'll just put this in here. Total delta P equals the area under an F versus time graph. In maths, that's of course the integral or the integration. So if you integrate force with respect to time, you get the delta P. So like this, the integral between 0 and t of force with respect to time, delta P. Which one of the devices would transfer the greatest moment to the glider? So what we need to do is look at which is going to have the largest area. And if I look at these, I can see that, let's see, has A got a larger area than B? Well, we can actually add the areas up. So A, we'll assume that that top point on the graph is 2 and the midpoint is 1, just for the sake of this. That allows us to, and the other one is T, so then we get 1.5 times T, that's a square piece, plus a half times T times 0.5. That's a half of, for the triangle, the upper triangle. So, and which in total is 1.5 plus a quarter, 1.75 times T. B, the area is just 1.5 times T. C, now this is a triangle from bottom to top, so this is a half times 2 times T, which is just 1 times T. D looks less than a triangle. I'm not going to try and figure out exactly what it is, but it's less than 1 times T. And E, now this is all below the bottom half, so it is less than 1 times T as well. So the correct answer is A, graph A, or the product A. Launcher A gives greatest momentum. Because it has the largest impulse calculated as area under the F versus T graph. That was question 3. Now question 4. The graph shows the force on a ball of mass 0.085 kilograms while being hit by a bat. The bat causes the ball to change its direction by 90 degrees. The speed of the ball as it approaches the bat is 9.6 meters per second. Calculate the change in momentum of the ball. Alright, well, let's just assume that we're going to be doing delta P equals PF minus PI. These are vectors. Let's just start there. Because it's changed direction, we're going to need vectors, right? The magnitude of PI is MV, which is 0.085 times 9.6, which is let's look, oops, 0.816 kilogram meters per second. Seems right. We can calculate the impulse, delta P, magnitude at least, based on the area of F versus T graph. And this is a triangle with a base of, so it's a triangle, so it's a half times base times height, which is a half times 0.050 times 40, which equals half times that is equal to exactly 1 kilogram. I'm going to put 1.0 because it's going to be two significant figures. So half times 40 is 20, and 20 times 0.050 is 1. 1.0 kilogram meters per second. So that's our magnitude. And we're going to need a vector diagram. So let's assume the ball comes in, changes direction by 90 degrees. So it comes in, changes direction by 90 degrees, because it said that, right? Change direction by 90 degrees. So here's the change in direction. So I'm just drawing this is not a vector diagram at this point, this is a path diagram. Okay, so there's our vector in and our vector out for this hitting the bat. Now we want to do our vector diagram, because we've got to use this one. Delta P equals PF, and it's negative PI, so minus PI, so it's plus negative PI. So as we do this, we've got to go delta P. We're going to do that last, obviously. So PF is down. Negative PI, well that's PI going to the right, so negative PI is going to the left. And that means that our, whoops, didn't draw that very well, did I? So this is delta P. And we have a magnitude for PI. And we have a magnitude for delta P. So we can use Pythagoras, we can use a whole lot of things to sort stuff out. We can work out the angle, and we can work out the magnitude, and we can use SOHCAHTOA and Pythagoras. And in this case we've got the hypotenuse, the adjacent and the opposite. So we're going to use, to find this one, we've got these two, to find the angle, we've got these two given so far, so we'll use the hypotenuse and the adjacent, that's this one, car. So cosine of theta equals the adjacent rather, 0.816 over 1.0. Theta equals cosine inverse of that. So that's 0. Whoops. Which is, when you get dumb answers, make sure you think about them. 35 degrees to two significant figures. And the magnitude we've already been given. So we're going to have to try and give this in some useful way. Like the problem is that, like, what direction is that? So if we put it on our graph here, this is the change in momentum, and here is the angle, and the amount of the change in momentum is 1.0. and the angle is 35 degrees. So that's my answer. Part B, calculate the speed of the ball as it leaves the bat. Well, here's our, if we've got our thing here, we can now calculate PF. So magnitude of PF equals, we can use Pythagoras' theorem. So PF squared equals 1.0 squared minus, let's just do this properly. Hang on. I'm sort of trying to skip ahead, which I would do if I was doing it just for myself, but I'm doing it for you, so I will just take every step that I should take. So Pythagoras to solve this gives you 1.0 squared equals PF squared plus 0.816 squared. Okay, so PF squared equals 1.0 squared minus 0.816 squared. PF equals the square root of 0.334144, which is 0.578 kilogram meters per second. That is not our answer because we've been asked for the speed of the ball as it leaves the bat. P equals mv. Therefore, V equals 0.578 divided by, so the momentum divided by, actually, again, go back, take the steps, make it less steps at once, makes less room for error. So P equals mv, 0.5, substitute first, 78 equals the mass, which we've been given, 0.085 times V. V equals 0.578 divided by 0.085, which is 6.8 meters per second to two significant figures. And I'll just quickly check all those answers to make sure I'm not giving you duds. Seven B. Yep, that's all good.